Welcome back to Sleepy Orbits. Maybe the house has finally gone quiet around you. Maybe you're lying in the dark listening to a fan turn. Or you're the only one awake on your street, one lit window in a row of sleeping ones. Wherever tonight finds you, you're in the right place. Tonight, we're going to spend some time with a single object. It sits 10.8 billion light-years away in the constellation Canes Venatici, just off the handle of the Big Dipper. It's called TON 618, and it is the heaviest black hole human beings have ever measured, around 66 billion times the mass of our Sun. You already know black holes are big. Everyone knows that. It's the first thing anyone learns about them. But here's the thing most people don't realize. TON 618 isn't just a bigger version of the black holes you've heard about. It's so large that it breaks the mathematics of how black holes are supposed to grow. Take everything we know about how these objects feed, give one of them the entire age of the universe to eat, and you still struggle to build TON 618. It shouldn't have had the time, and yet its light is right there on our photographic plates, and has been since 1957, when astronomers mistook it for a faint violet star and filed it away without a second look. By the end of tonight, the word big is never going to sound quite the same. One thing before we begin: if you fall asleep partway through, good. That's the point. In the morning, tell me in the comments the last thing you remember hearing, and if you make it to the end, tell me which part of TON 618's story stayed with you and what you'd like us to explore next. If these nights help you rest, a like or a subscribe helps this channel more than you'd realize. Now, let's begin. Before we can understand what makes TON 618 wrong, we need to be honest about what makes an ordinary black hole right. Start with the one you live with. At the center of our galaxy, about 26,000 light-years from your bed, there is a black hole called Sagittarius A star. Every star you have ever seen, every star anyone has ever seen with the naked eye in the whole history of people looking up, orbits it. The Sun has been circling it since before the Sun had planets. One full lap takes around 230 million years. The last time we were on this side of the orbit, the deserts of Pangaea hadn't yet broken into continents, and the first dinosaurs were only just learning to be dinosaurs. Sagittarius A star weighs about 4.3 million times as much as our Sun. 4.3 million. Hold on to that number. It sounds enormous, and it is. It's the anchor of 200 billion stars. Proving it was there took nearly 30 years of one of the most patient campaigns in the history of science. The center of our galaxy hides behind vast banks of interstellar dust. Invisible light, we simply cannot see it at all. So two rival teams, one led by Reinhard Genzel in Germany using telescopes in the Chilean desert, the other by Andrea Ghez using the Keck telescopes on a volcano summit in Hawaii, watched it in infrared light instead, which slips through the dust. Year after year, decade after decade, they photographed the same small patch of sky and tracked a handful of stars circling something invisible. The stars traced out perfect closed ellipses, textbook orbits, around a point that emitted almost nothing. One of them, a star called S2, swings through the bottom of its orbit at more than 7,000 kilometers per second, completing a full loop every 16 years. Both teams, working independently, competitively, with different telescopes on different continents, converged on the same answer to within a few percent. The measurements were so precise and the conclusion so unavoidable that the work earned the 2020 Nobel Prize in Physics. There is a compact, dark, 4 million solar mass object at the heart of the Milky Way, and nothing but a black hole fits the data. I mention the 30 years deliberately. Everything in tonight's story rests on measurements like these, long, quiet, unglamorous campaigns of watching. Whenever a number like 66 billion solar masses gets said out loud, somewhere behind it is a person on a mountain, checking the same patch of sky for the 10,000th night. And here is the strange part. For all that mass, Sagittarius A star is small. Its event horizon, the boundary past which nothing returns, not matter, not light, not information, would fit comfortably inside the orbit of Mercury. If you replaced the Sun with it tonight, the Earth wouldn't be pulled in. We'd freeze in the dark, but our orbit would barely notice. Black holes don't reach out and grab. They only ever accept what falls. That's the first correction to the picture most of us carry. A black hole is not a cosmic vacuum cleaner. It is a place where too much mass gave up on being anything else. Squeeze any amount of matter into a small enough space, and its gravity wins every argument physics knows how to have. The matter collapses. What's left behind is not a surface, not a thing you could touch, but a region, a boundary drawn in empty space, marking the line where escape stops being possible. The size of that boundary is set by one thing only: mass. The physicist Carl Schwarzschild worked out the mathematics in 1916, within weeks of Einstein publishing General Relativity, working, remarkably, from the Russian front of the First World War in the last year of his life. Every black hole has a Schwarzschild radius. Double the mass, and the radius doubles. It is one of the cleanest scaling laws in all of physics, and it means something useful for tonight. When we say a black hole is heavier, we are also saying, in exact proportion, that it is bigger. Let's meet the whole family before its largest member, because black holes come in a strange, gappy range of sizes, and the gaps matter as much as the sizes. At the small end are the stellar mass black holes, the corpses of giant stars. The first one ever confirmed orbits a blue supergiant in the constellation Cygnus, a system called Cygnus X1, about 7,000 light-years away, discovered as an X-ray source in the 1960s. The black hole there weighs around 21 solar masses, and it's close enough, in cosmic terms, to feel like a neighbor. The physicist Stephen Hawking once bet against it being a black hole at all. He lost and paid up cheerfully, saying it was the kind of bet you're glad to lose. Our galaxy is scattered with these objects. Statistical estimates suggest the Milky Way contains something like 100 million of them, quiet, starless points drifting between the constellations, almost all of them unseen and permanently unseeable except when something falls in. 100 million black holes just in our galaxy. 10 or 20 suns apiece. Then there is a gap, a strange one, between the heaviest stellar black holes, a few dozen suns, and the lightest of the giants. The record is nearly empty. Black holes of 1,000 suns, 10,000, 100,000, the so-called intermediate mass black holes, should exist if the giants grew from the small ones. They would be the teenagers of the family, the missing rungs on the ladder. And for decades, astronomers have found only scattered, disputed candidates. A few promising ones sit in dense star clusters. The gravitational wave observatories have caught black holes colliding to form objects of 100 and some suns right at the gap's lower edge. But the middle of the ladder remains strangely bare, a detail worth tucking away, because it will come back to haunt us later tonight when we ask how the giants were made. And then at the top of the ladder, in the center of essentially every large galaxy we've ever examined closely, the supermassive black holes, millions to billions of suns, not scattered through the galaxy like their small cousins, but enthroned, one per galaxy, at the exact center of the whole system's turning. So, 4.3 million solar masses, a horizon smaller than Mercury's orbit. That's our galaxy's own giant, our local top of the ladder. Now go bigger. In the spring of 2019, the Event Horizon Telescope collaboration showed the world the first photograph of a black hole. That soft, orange ring you have almost certainly seen, glowing like a blurred ember. That object sits at the center of a galaxy called Messier 87, 55 million light-years away. It weighs about 6.5 billion solar masses, 1,500 times the mass of Sagittarius A star. Its event horizon is larger than our entire solar system. The bright ring in that photograph is hot matter circling a darkness you could drop every planet, moon, comet, and probe humanity has ever known into without it touching the sides. 6.5 billion suns. Astronomers had to reach for a new word for objects in this class. Beyond supermassive, a black hole above about 10 billion solar masses is sometimes called ultramassive. It is not an official term so much as an admission, an acknowledgement that the vocabulary was running out. M87's black hole felt for a while like the reasonable ceiling. Big galaxies grow big black holes. The biggest nearby galaxies had black holes of a few billion suns. The scaling made sense. The universe seemed to have a speed limit on how monstrous these things could get, and the numbers we were finding respected it. Ton 618 weighs roughly 10 times as much as the black hole in that photograph. 10 times the object that needed a telescope the size of the Earth to see. 10 times the mass that already had astronomers reaching for new words. 66 billion solar masses, more by some measures than every star in the Milky Way combined. Our entire galaxy's worth of starlight, of stellar nurseries, and red giants and white dwarfs, and every sun that has ever warmed anything here. Take all of it, press it together, and you still come up short of this one dark object on the far side of the universe. And unlike Sagittarius A star, quietly anchoring its stars, Ton 618 announced itself. It announced itself so loudly that we heard it across 10 billion light years, and then spent 13 years thinking it was nothing at all. That's where the story actually begins, not with a monster, with a smudge. In 1957, on a dark hillside in the Mexican state of Puebla, there was an observatory called Tonantzintla. The name comes from Nahuatl, the language of the Aztecs. It means place of our little mother. The telescope there was modest by the standards of the great American observatories, a Schmidt camera with a mirror about 70 centimeters across. Not a giant, a workhorse. Two astronomers, Braulio Iriarte and Enrique Chavira, were using it for a survey, patient, unglamorous work of exactly the kind that fills most real careers in astronomy. They were photographing the sky far from the plane of the Milky Way, hunting for faint blue stars. Blue matters in that kind of search. Most faint stars are red and cool. A faint star that burns blue is usually something interesting. A white dwarf, a hot subdwarf, some small, strange thing in our own galactic neighborhood. The survey worked the old way, glass photographic plates exposed in the telescope through the long Mexican night, developed by hand, then examined dot by dot. Thousands of specks of silver on glass, each one a star, each one needing a human eye to notice it, judge its color, and write it down. Entry number 618 in the Tonantzintla catalogue was one of those specks. In their notes, it stood out enough to earn a small remark. The object appeared, they wrote, decidedly violet. Decidedly violet. That was all. A faint dot, bluer than it had any right to be, sitting in the constellation Canes Venatici, the hunting dogs just below the handle of the Big Dipper. It received a number, a line in a catalogue, and no further attention. Both men went on with the survey. The plate went into an archive, and the most massive black hole ever measured sat in a drawer, labelled as a star for 13 years. There's no shame in that, by the way. Pause on it for a moment because it tells you something about how discovery actually works. In 1957, the correct interpretation of that dot did not exist yet. Not wasn't known, did not exist. The word quasar hadn't been coined. No one on Earth had ever conceived of an object that could shine across billions of light years. If Iriarte and Chavira had somehow guessed the truth and published it, no one would have believed them, and they would have been right to be doubted. The universe was about to get drastically larger, and nobody knew it yet. The change came in 1963. Radio astronomers had been finding sources of radio noise in the sky that matched what looked like ordinary faint stars. One of them, catalogued as 3C273, was driving everyone quietly mad. Its spectrum showed bright emission lines that matched no known element. At the Palomar Observatory in California, a Dutch astronomer named Martin Schmidt sat with that spectrum and saw what everyone had been missing. The lines weren't from an unknown element. They were the most familiar lines in astronomy, the fingerprint of plain hydrogen, but shifted, stretched toward the red end of the spectrum by almost 16%. In an expanding universe, that kind of stretch means one thing: distance, enormous distance. 3C273 wasn't a faint star in our galaxy. It was something 2 billion light-years away, shining so ferociously that it looked like a nearby star. Do the arithmetic on brightness and distance, and the object had to be pouring out hundreds of times the light of our entire galaxy, from a region small enough to flicker in months, meaning it could only be light months across. The astronomers called these objects quasi-stellar radio sources. The name got worn down by use, the way names do, into quasar. Almost nobody could accept, at first, what quasars implied. Whole conferences argued about it. Something smaller than the solar system, outshining 100 billion stars. What engine in physics could do that? Stars couldn't. Nothing made of ordinary burning could. The resistance was serious, and it lasted years. This wasn't a fringe squabble. It was a genuine crisis. A respected school of astronomers argued that the redshifts had to be misleading, that quasars weren't distant at all, but nearby objects flung out of ordinary galaxies at great speed, their light stretched by motion rather than by the expansion of the universe. If that were true, quasars could be small, modest things, and physics could relax. The astronomer Holton Arp spent much of his career assembling photographs of quasars that appeared suspiciously close to nearby galaxies, arguing the alignments couldn't be chance. It was a real debate, conducted by capable people, and it deserves better than mockery, because the orthodox position genuinely was extraordinary. Believing the redshifts meant believing in engines 1 trillion times brighter than the sun. Doubt was the reasonable first response, but the evidence kept arriving, and it all pointed one way. Quasar spectra showed absorption lines from gas clouds at every distance between us and them. You don't pass through 10 billion light-years of fingerprints unless you're 10 billion light-years away. Deep images began to reveal the faint fuzz of host galaxies around quasars at exactly the distances the redshifts demanded. And then gravity itself testified. Astronomers found quasars whose light had been split into multiple images by the gravity of a galaxy sitting in front of them. Gravitational lensing, impossible unless the quasar truly sat far behind the lens. The universe had countersigned the redshifts. So, the distances stood, and the engine problem had to be faced head-on. Slowly, over the following decade, the only workable answer emerged, and it was the one that sounded the most like science fiction: a giant black hole feeding. Here is the idea, and it's worth settling into because it powers everything else tonight. A black hole on its own is dark, the darkest thing possible. But a black hole surrounded by gas is another matter entirely. Gas falling toward the horizon doesn't drop straight in, any more than water falls straight down a drain. It spirals. It flattens into a disk, orbiting at a good fraction of the speed of light on the inside edge. And in that disk, friction goes to work. Each ring of gas rubs against the rings beside it, and the rubbing heats the disk to hundreds of thousands of degrees until it glows, not with fire, which is chemistry, but with the raw thermal blaze of matter being wrung out by gravity. It turns out to be the most efficient large-scale engine in the universe. The nuclear fusion that powers the sun converts about 7/10 of 1% of matter's mass into energy. An accretion disk around a black hole can convert several percent. In some cases, with a rapidly spinning black hole, theoretical efficiencies approach dozens of times that of fusion. Matter's last act, before vanishing forever, is to shine brighter than it ever could as a star. So, a quasar is a paradox with a simple anatomy. The brightest, sustained light in the universe produced by the darkest object in the universe at the moment of feeding. The blaze is the scream of everything the black hole is about to swallow. In 1970, a radio survey conducted at Bologna in Italy swept across Canes Venatici and found radio emission coming from the position of a certain faint violet dot. Catalogue entry 618 from Tonantzintla was not a star. It was one of these new monsters. The blue-violet light that Iriarte and Chavira had noted on their glass plate was the glow of an accretion disk, light that had been traveling toward that Mexican hillside for 10.8 billion years. Think about what that number means for a moment, because it's easy to say and hard to hear. The light on that 1957 photographic plate left ton 6, 18, 10.8 billion years ago. The Earth is 4.5 billion years old. That light had already been traveling for more than 6 billion years before there was an Earth to aim at. It crossed the darkness while our sun was still an uncollapsed cloud, while the Milky Way was still assembling itself out of smaller galaxies, while every atom in your body was still scattered through interstellar space waiting to be gathered. It arrived at the end of its journey on a winter hillside in Puebla, passed through a 70-centimeter mirror, and became a violet speck on a piece of glass, noted, numbered, and misunderstood. When the spectroscopes finally turned toward it in earnest, they measured its redshift at 2.219. Its light stretched to more than 3 times its original wavelength by the expansion of the universe itself. And when they worked out how luminous something at that distance would have to be to appear even as a faint dot, the answer came back at roughly 140 trillion times the luminosity of the sun, 140 trillion suns. From one object, it is among the most luminous things ever catalogued, and the engine driving it, the dark mass at the center of all that light, had to be weighed to be believed. Before we weigh it, though, it's worth understanding the era it belongs to, because Ton 618 did not blaze alone. It comes from a time astronomers have taken to calling cosmic noon, and the name is exactly right. When surveys began cataloguing quasars by the hundreds and then by the hundreds of thousands, a pattern emerged in their distances. Quasars are rare in today's universe. The nearby cosmos is quiet. They're also rare in the very earliest universe we can see. But in between, there is a crescendo. The population of blazing galactic centers rises as you look further back, peaks, and then falls away again toward the dawn. The peak, the loudest moment in cosmic history, sits at a redshift of roughly 2, the epoch when the universe was around 3 billion years old. TON 618's redshift is 2.219. It lived at the summit of that curve. We are seeing it at the exact height of the universe's most violent age. And the age makes sense once you know what feeds a quasar. 3 billion years in, the universe had everything a monster needs. Galaxies were young, gas-rich, and packed closer together. The cosmos was smaller then, remember. Everything has been spreading apart ever since. Collisions were constant, and a collision is a feeding event. When galaxies merge, their gas loses its orderly orbits and pours toward the center, straight into the lap of whatever waits there. Cosmic noon was billions of years of galaxies crashing into each other, while their central black holes fed on the wreckage. The sky of that era, could you have seen it all at once, was lit with quasars, the way a summer field is lit with fireflies, each spark a galactic center in the act of devouring. Then the universe spread out, the collisions grew rare, the gas ran thin, and one by one the fires went dark. The quasar era ended. The monsters remained hidden, hungry and quiet. And today we find their descendants sleeping at the center of every great galaxy, including ours. Here's the part of the quasar story I find genuinely moving, though. Before they were understood, quasars were an embarrassment, objects too bright to explain, an argument at every conference. Once they were understood, they became something else entirely. Lighthouses. A beam that crosses 10 billion light-years doesn't just tell you about its source. It illuminates everything it passes through. Astronomers learn to read the shadows in quasar light, the absorption fingerprints stamped on it by every invisible cloud of hydrogen it traversed on the way to us. Whole maps of the ancient universe, gas that never formed stars, that no telescope could ever see directly, exist only because quasar light passed through it, like headlights through fog. The universe's most violent objects became its most useful street lamps. TON 618 is one of the brightest of them all. Its light has been interrogated for decades, not only for what it says about the monster, but for what it accidentally recorded on the journey. 10.8 billion years of cosmic weather, pressed into a spectrum like flowers in a book. But tonight, we care about the source, and so we owe this object something more basic. We've been saying 66 billion solar masses, as though a number that size can just be said. It can't. Numbers like that slide off the mind like water off glass. If tonight is going to mean anything, we need to actually feel the size of this thing, to walk up its scale step by step, slowly, the way you'd wade into cold water. So let's do that now. Let's go there. Every attempt to describe Ton 618 runs into the same wall. There is nothing in human experience to compare it to. So we're going to build the comparison from scratch, starting with things you know, and we are not going to hurry. Start with the Earth. Not the idea of the Earth, the actual size of it. If you've ever flown across an ocean, you know that particular boredom, the hours of nothing but water. A commercial jet needs the better part of a day to cross the Pacific. Walking, you'd need years. The Earth is, by every standard your body understands, enormous. The Sun could hold 1,300,000 Earths. That's the first step, and it's already absurd. If the Earth were a grape, the Sun would be a sphere taller than a 2-story house. Every ocean, every mountain range, every city and desert and ice cap you have ever seen pictures of, 1,300,000 of all of it, to fill the Sun once. Now the solar system, light, the fastest thing there is, the universe's own speed limit, leaves the Sun and reaches the Earth in about 8 minutes. It passes Mars a few minutes later. It reaches Jupiter in about 3/4 of an hour, Saturn well over an hour, and Neptune, the last of the planets, doesn't see that light until more than 4 hours after it left the Sun. 4 hours? At 300,000 kilometers every second. That is the radius of the neighborhood we live in, the distance across the Sun's family of planets. Hold that 4 hours in your mind. In 1977, we launched a spacecraft called Voyager 1. It is the fastest long-distance object human beings have ever sent anywhere. And it has been traveling without a single day off for very nearly 50 years. It crossed Jupiter's orbit in under 2 years. It passed Saturn in 3. It has been climbing away from the Sun ever since, out past the planets, through the boundary where the solar wind gives way to interstellar space. After half a century of continuous flight, Voyager 1 is now a little less than 1 light day from home. Light that leaves the Sun catches up to Voyager in about 23 hours. 50 years of flight. Not quite 1 day of light. Now we're ready. Now the numbers mean something. Let's approach Ton 618. The event horizon of Ton 618, the boundary of the darkness itself, not the glowing disk around it, just the sphere of no return, has a radius of roughly 1,300 astronomical units, 1,300 times the distance from the Earth to the Sun. In more honest units, the horizon sits about 40 times farther out than Neptune. The entire solar system, the Sun, all 8 planets, every orbit you've ever seen drawn in a textbook, could be dropped into Ton 618, and it would be a detail, a fleck. Our whole planetary neighborhood next to that horizon is roughly what a coin is to a football pitch. Light crossing the Sun's family of planets takes those 4 hours we held on to. Light crossing Ton 618 entering at one side of the event horizon's diameter and reaching the other would need around 2 weeks. 2 weeks at the speed of light. Let that be more than words for a second. Sunlight reaches your face across 150 million kilometers in the time it takes to brew tea. That same light, set loose across the diameter of this one object, would fly day after day after day, a full week, then another, before reaching the far side. If the light set out on a Monday, it would arrive at the opposite edge somewhere around the Monday after next. There are entire holidays shorter than the time light needs to pass this single thing. And Voyager, our fastest, farthest traveler, 50 years out from home. At its current speed, if it were crossing ton 618 instead of leaving the solar system, its half-century of flight would have covered about 6% of the way across. Every engineer who built it, every scientist who launched it, and nearly every person alive to watch it leave would grow old and pass on, generation after generation, before it was even a tenth of the way through the dark. Now, and this is where I'd like you to actually come with me for a while, imagine we could make the journey ourselves. No ship, no rush, just you drifting the way you're lying there now toward ton 618 from far away. Let's see what it would actually be like. From a great distance, the first thing you notice isn't the black hole, it's the light. Long before the darkness resolves into anything, there is a point ahead of you, glowing with a pale, hard, blue-white brilliance, brighter than any star could be, steadier than any flame. It doesn't flicker, it doesn't twinkle, it simply pours. You are seeing the accretion disk from far away, 140 trillion suns worth of shine compressed into a dot. And even from here, from farther away than you can hold in your head, it is bright enough to cast your shadow behind you into intergalactic space. You drift closer. It takes a long time. Everything about this place takes a long time. And the dot slowly widens into a shape. A disk, tilted, immense, glowing white at its heart, and shading through violet blue to a deep smoldering orange at its far edges, like a vinyl record made of lit gas spinning. It is larger than any structure you have ever imagined. Storm patterns bigger than galaxies' worth of weather ripple across it in slow motion. Streams of gas the size of solar systems peel off its inner edge and vanish. And in the middle of all that light, you begin to see it. A circle of perfect nothing. Not black like a night sky, which always has some faint glow to it. Not black like a dark room, where your eyes eventually adjust. This is the black of absence, a region that gives your eye nothing at all, ever, no matter how long you stare. The disk's light bends around it in a thin, impossibly sharp ring, because the black hole's gravity curves the paths of the photons themselves, wrapping the light of the far side around the darkness like a halo. You are looking at a hole in the visible universe, 40 Neptune orbits deep in every direction. Here is the strangest part of the visit. If you kept drifting, If you crossed the horizon of Ton 618 itself, the crossing would be gentle. That sounds wrong, so let's take it slowly. Near a small black hole, the one thing everyone has heard about is real: the tides. Gravity pulls harder on your feet than your head. The difference becomes violent, and anything that falls in and is stretched and shredded long before the horizon. Physicists genuinely call it spaghettification, which may be the only whimsical word in general relativity. But tidal force depends on how sharply gravity changes from point to point. And around a truly enormous black hole, the curvature at the horizon is spread across such a vast distance that the change across a human body is almost nothing. The bigger the black hole, the gentler its edge. At the horizon of Ton 618, the pull on your feet and the pull on your head would differ so little that you would feel no tug at all, no jolt, no boundary, no sign of any kind that you had just crossed the most final line the universe knows how to draw. The stars behind you would go on shining. You would feel like you were still simply drifting, and nothing in physics, no engine, no signal, no prayer, could ever bring you back. What would be on the other side of that gentle crossing? Physics has an answer, and it is stranger than any monster story, because inside a black hole, space and time trade places. Outside the horizon, you can move freely through space, but time carries you helplessly forward. You can pace around your bedroom all you like, but you cannot pace away from Tuesday. Inside the horizon, the mathematics of relativity says the roles reverse. The center of the black hole stops behaving like a place, a point you could steer around, and starts behaving like a moment, like Tuesday. The center is not somewhere ahead of you, it is when ahead of you. Every path through space, every direction you could face, every burn of every engine leads there, for the same reason that every possible choice you make tonight still leads to tomorrow morning. Falling to the center isn't like falling to the ground, it's like aging. And for Ton 618, we can even say how long you'd have. The bigger the black hole, the longer the interior lasts for the one falling through it. Cross the horizon of a small, stellar black hole, and your remaining time is measured in microseconds. Cross the horizon of Ton 618, and the mathematics grants you on the order of a week or more of existence inside, days of drifting through the largest enclosed volume in the known universe, the stars behind you still faintly visible in the distorted sky before the end arrives. A week inside the dark. It is the only place in nature where the phrase "living on borrowed time" is not a metaphor, but a calculation. What actually waits at the center? The singularity. The point where the equations record infinite density and then refuse to say anything more. Nobody knows. General relativity predicts its own breakdown there. The infinities are widely read not as a description of reality, but as the theory politely handing in its resignation. Whatever truly sits at the heart of Ton 618 belongs to a physics we don't have yet. the same unfinished quantum gravity that guards the first moment of the Big Bang. The largest black hole we've ever measured keeps at its center the smallest and best hidden secret in the universe, and time itself would have begun to change around you. This is real, measured physics, not poetry. Though near an object like this, the two become hard to tell apart. Gravity slows time. Not as a metaphor, clocks genuinely tick slower the deeper they sit in a gravitational well. We've measured it on Earth, where the difference between your head and your feet, a meter of height in our planet's modest gravity, amounts to a fraction of a second across an entire lifetime. Your head is aging faster than your feet right now by an amount too small to ever feel. The satellites that carry the GPS system experience it strongly enough that, without correcting for their faster ticking clocks, every map application on Earth would drift by kilometers within a day. Time dilation is not exotic. It's an engineering constraint. Near ton 618, it stops being subtle. As you drifted closer to that horizon, your time and the universe's time would quietly come apart. To you, nothing would change. Your heartbeat, your breathing, your thoughts, all normal. But if you looked back at the universe behind you, you would see it subtly quickening, stars aging faster than they should. Distant clocks racing, hover close enough to the horizon, and years could pass outside for every day you experienced. The black hole would be, in the most literal sense physics allows, a place where you could stand aside from time, where the universe's whole story would rush past like a river past a stone. And to the universe watching you, you would appear to slow and dim and redden, your image stretching over longer and longer intervals as the light climbing away from you lost more and more of its strength until you faded from view entirely, your last moment before the horizon smeared across eternity. From the outside, nothing is ever seen to fall in. The universe keeps a slowing, fading photograph of everything the black hole has ever taken. Somewhere in the light of ton 618, in the outermost, faintest, most stretched fringes of it, that photograph album exists. Every star and cloud it has swallowed for billions of years, frozen mid-fall. There's one more strangeness worth taking to bed tonight. If you take the mass of ton 618 and spread it evenly through the volume enclosed by its horizon, just arithmetic, mass divided by volume, the density you get is lower than the density of the air in the room where you're lying. That is not a trick. It's a real feature of how these objects scale. The radius grows in step with the mass, so the volume grows much faster, and the average density falls and falls. A small black hole is denser than anything imaginable. An ultra-massive one, by this averaged measure, is thinner than air, thinner than mist, a region of near nothing so large that its combined gravity still closes the door on light. Ton 618 is not a dense knot of matter in any ordinary sense. It is an emptiness so wide that the universe cannot climb back out of it. So that's the scale of the thing. A horizon 2 weeks wide at light speed, a solar system reduced to a coin on a pitch, a crossing so gentle you'd never know, and an interior, averaged out, thinner than your bedroom air. Which brings us, finally, to the question that should have been bothering you all along. How could anyone possibly know how much it weighs? Nobody has ever photographed TON 618's horizon. It is thousands of times too far away for that. Nobody has watched stars orbit it, the way Genzel and Gez watched S2 whip around our own galactic center. Everything we know about the mass of this object was deduced from a smear of light on a spectrograph, from reading in the stretched fingerprint of hydrogen the speed of the storm around the dark. That measurement is one of the quiet triumphs of modern astronomy. It's also where the certainty starts to soften. And being honest about that is part of tonight's story too. Here is the problem, stated plainly. You have a dot of light. It does not move across the sky in any measurable way, and it never will in a human lifetime. You cannot see the object inside it. You cannot visit. You cannot send a probe, bounce a signal, or wait for it to pass in front of anything. 10.8 billion light-years is not a distance across which anything can be touched, and yet astronomers will tell you its central mass to within a factor of 2. How? The first thing to rule out is the obvious idea, just photograph it, the way the Event Horizon Telescope photographed M87. It can't be done. And the reason why is a useful piece of humility. That famous orange ring took a telescope with the effective size of the entire Earth, radio dishes from Hawaii to Spain to the South Pole, observing in perfect synchronization their data flown together on pallets of hard drives and combined into a single virtual instrument. All of that machinery was needed to resolve M87's horizon at 55 million light-years. TON 618 is 200 times farther away, and although its horizon is 10 times wider, the arithmetic is Ursulus. It appears tens of times smaller in our sky than the smallest thing the Earth-sized telescope can see. To photograph TON 618's shadow, you would need a telescope bigger than the Earth, dishes standing in space, spread across a region wider than the planet. Perhaps someone will build that someday. Nobody has built it yet, so there is no picture, and there will be none in our lifetimes. The weighing had to be done another way, and the answer begins with a simple, ancient piece of physics. The heavier the thing you orbit, the faster you must move to keep from falling in. The Earth orbits the Sun at about 30 kilometers per second. Mercury, deeper in the Sun's grip, moves at nearly 50. That star S2 skimming past Sagittarius A star hit more than 7,000 kilometers per second, and it was precisely that speed at that distance that let astronomers put our galaxy's black hole on a scale. Orbital speed is a weighing machine. If you can clock how fast something circles and how far out it is, the mass in the middle falls out of the mathematics of gravity that Newton wrote down 3.5 centuries ago. So the question becomes, is anything orbiting TON 618 that we can clock? There is. The quasar's own fuel. Around the accretion disk of a quasar, farther out than the blinding inner engine, there are vast clouds of gas, a region astronomers call, with unusual descriptive honesty, the broad line region. These clouds are lit up and energized by the disk's ferocious light, and they respond the way all energized hydrogen responds. They glow at precise, fixed wavelengths. The fingerprint of hydrogen again, the same handful of spectral lines that gave Martin Schmidt his revelation in 1963. Fixed wavelengths, though, only stay fixed if the gas is standing still. These clouds are not standing still, they are orbiting the black hole, some swinging toward us as they circle, some swinging away. The light from the approaching clouds is compressed to slightly shorter wavelengths. The light from the receding clouds is stretched to slightly longer ones. It's the same physics that bends the pitch of a passing siren, the Doppler effect, working on light. So when the light from all those clouds arrives together, mixed into a single spectrum, that once sharp hydrogen line arrives smeared, broadened into a wide hill instead of a narrow spike. And the width of that hill is a speedometer. The broader the line, the faster the storm of gas is circling the center. Read the hydrogen beta line in the spectrum of TON 618, and the broadening tells you the clouds are moving at speeds up to 7,000 kilometers per second, 7,000 kilometers every second, London to New York in less than a heartbeat. And these are not stars being slingshotted on a close pass. These are continent-sized weather systems of gas in ordinary long-term orbit at distances from the center measured in light years. The speedometer, though, is only half of the weighing machine. To turn a speed into a mass, you also need to know how far from the center the speeding gas orbits. The size of the racetrack, not just the pace of the runners. And the racetrack from 10 billion light years away is hopelessly too small to see. Even our best telescopes register the whole broad line region as a single unresolved point. The solution astronomers found is, I think, one of the most elegant tricks in the whole science. It's called reverberation mapping, and it works like this. Quasars flicker. The central disk brightens and dims irregularly on timescales of weeks and months, and every time it flickers, the glowing clouds around it respond, but not instantly. The clouds can only answer when the changed light reaches them, so the echo of each flicker arrives in the spectrum after a delay, and the delay is the light travel time from the disk to the clouds. Watch a quasar patiently, for months, for years, and the lag between the flicker and its echo hands you the radius of the racetrack, measured in light days or light weeks or light years, using nothing but a calendar. Astronomers weigh the heaviest objects in the universe with a stopwatch. For the biggest quasars, that echo delay can run to months or years. Around TON 618, the glowing storm orbits at distances where the disk's own light needs a substantial fraction of a year to reach it. Speed from the width of a spectral line, distance from the timing of an echo, Newton's arithmetic to bind them together. Run it all for TON 618 and the answer comes back in the tens of billions of solar masses. The landmark measurement published in 2004 put it at 66 billion suns. And TON 618 entered the record books as the heaviest black hole ever weighed. Now for the honesty. That number is an estimate, and astronomers would be the first to say so. The weighing method rests on assumptions you can't fully check from 10 billion light-years away. How far from the center is the glowing gas exactly? The distance has to be inferred from the disk's brightness, not measured directly. Are the clouds moving in tidy circular orbits, or is some of that speed gas being blown outward by the quasar's own radiation? Is the region tilted toward us or side on? Each of those uncertainties feeds into the final mass. In 2019, a team led by the astronomer Schwege revisited ultra-massive quasars with refined methods and revised TON 618's likely mass downward to around 40 billion solar masses, 40 billion instead of 66. It's worth sitting with what kind of correction that is. The mass of 26 billion suns, 4,000 Milky Way central black holes, is the error bar. The uncertainty alone, the wobble in our knowledge, outweighs every black hole in our corner of the universe put together. Is it even still the champion? Honesty requires a word about the competition. In 2019, a good year for giant black holes, astronomers weighed the central black hole of a galaxy called Holmberg 15A in a cluster 700 million light-years away, using the motions of the stars around it, about 40 billion solar masses, and measured by a more direct method than TON 618's. Depending on which estimate of TON 618 you prefer, Holmberg 15A is either the runner-up or the rightful record holder. And beyond both of them floats a phantom, an object in the Phoenix Galaxy cluster, sometimes claimed in preliminary, never quite confirmed analyses to hold as much as 100 billion solar masses. The claim is widely repeated online and weakly supported in the literature, treated as a rumor the universe hasn't confirmed. What's not in dispute is the class. A handful of objects scattered across the deep sky have grown to tens of billions of suns, and TON 618 remains the most famous, the best studied, and by the classic measurement the heaviest of them all. And here's the thing, the exact ranking doesn't matter for tonight's mystery. Whether TON 618 holds 40 billion solar masses or 66, both numbers live in the same impossible territory. Both make it one of the heaviest objects ever measured. Both leave its horizon wider than a light week. And both run headlong into the problem we've been circling since the hook, because the universe, it turns out, has rules about how fast a black hole is allowed to grow. It's time to talk about why this thing shouldn't exist. Black holes are not born big. That's the first rule, and everything else follows from it. The classic way to make a black hole is to kill a giant star. A star 20 or 30 times the mass of the sun burns furiously, exhausts its fuel in a few million years, and collapses, its core folding in on itself in less than a second, while the rest is blasted outward as a supernova. What's left at the center is a black hole of maybe 5, 10, 20 solar masses, nature's standard model. We've counted many of them in our own galaxy, so there's the starting kit, a black hole of a few dozen suns at best, and Ton 618 weighs tens of billions. The question is brutally simple. How do you get from 20 to 66 billion? The obvious answer is, it eats. Black holes grow by swallowing gas, and a quasar is precisely a black hole at dinner. Given enough gas and enough time, surely anything can grow to any size. But here's what most people never hear. Eating has a speed limit. Think about what feeding actually looks like for a black hole. The infalling gas forms that glowing disk, and the disk shines. Remember, it's the most efficient engine in the universe, blazing with the energy of everything being consumed. Now, light is not a passive thing. Light pushes. Every photon that flies outward from the disk presses against the gas that is still trying to fall in. The brighter the meal, the harder the push. So a feeding black hole is caught in a beautiful, self-defeating loop. The faster it eats, the brighter it burns. The brighter it burns, the harder its own light shoves the next mouthful away. Push the feeding rate high enough, and the outward blast of radiation exactly balances the inward pull of gravity on the infalling gas, and the meal stalls. Dinner blows itself off the table. That balance point has a name, the Eddington limit, after the great British astrophysicist Arthur Eddington, who worked out the physics of radiation pressure a century ago. It scales with the black hole's mass. A heavier black hole can eat proportionally faster, but at every size the limit is there. Feeding at the Eddington limit, a black hole can roughly double its mass every 40 million years or so. That's the throttle the universe sets, not a suggestion. A consequence of light itself fighting back. 40 million years per doubling sounds leisurely, but doubling is a powerful thing. Start with a 10 solar mass black hole and let it double, and double, and double. 10 becomes 20, 20 becomes 40. Keep perfect Eddington limited feeding going, and never a pause, never a disruption, and in about 30 doublings, you're at 10 billion solar masses. 30 doublings at 40 million years each is about 1.2 billion years of flawless, uninterrupted gorging. On paper, then, it can just about be done. The universe is 13.8 billion years old. 1 billion and something years of feeding fits inside that. If Ton 618 were a nearby object, if we were seeing it as it is today after the universe's full run, its mass would be merely astonishing rather than troubling. But we're not seeing it today. That's the trap the light springs on us. We are seeing Ton 618 as it was 10.8 billion years ago, when the universe itself was only around 3 billion years old. Now run the arithmetic with that deadline and feel it tighten. The first stars did not form instantly. The universe needed a few 100 million years to cool and gather them. So, the first stellar mass black holes, the 20 solar mass seeds, appear at the very earliest a few 100 million years in. To become Ton 618 by the moment, whose light we're seeing, a seed has roughly 2 to 2.5 billion years to grow from 20 suns to tens of billions. That requires feeding at the Eddington limit, the absolute physical throttle, essentially without interruption, for the entire history of the universe up to that point. And feeding without interruption is not how anything in nature behaves. Real galaxies are messy. Gas supplies stutter and run dry. Supernovae blow the fuel out of the neighborhood. Galaxy collisions scatter the pantry as often as they stock it. And the quasar itself, remember, spends its whole meal actively shoving its food away. Every simulation of these systems shows feeding that flickers, chokes, restarts. Asking a black hole to hold the throttle wide open for 2 billion years is like asking a candle to stay lit at maximum brightness, outdoors, through 2 billion years of weather. And yet, 66 billion suns, or 40, take your pick, sitting there in the spectrum, 3 billion years after the beginning. The light doesn't care that it's inconvenient. Something happened around that object that our tidy story doesn't capture. Astronomers, it should be said, love this kind of problem. This is the good kind of wrong. And the problem has a history. It has been tightening ratchet click by ratchet click for 25 years. The first clicks came around the turn of the millennium from a project called the Sloan Digital Sky Survey, a dedicated telescope in New Mexico that set out to map a quarter of the entire sky and take the spectrum of everything interesting in it. Sloan was a quasar finding machine, and it began turning up quasars at redshift 6 and beyond. Objects shining less than 1 billion years after the Big Bang, with black holes already at 1 billion solar masses. Each one was a small scandal. Then came the record breakers, culminating in a quasar called J0313, discovered at redshift 7.6, its black hole weighing around 1.6 billion suns when the universe was just 670 million years old, 7% of the universe's current age, and the monster was already 1,600 Sagittarius A stars. And remember that curious gap in the black hole family, the missing middle rungs of the ladder, the absent thousands of suns objects. This is where that absence starts to feel less like an accident and more like a clue. If the giants grew step by step from small stellar seeds, the universe should be littered with the in-between sizes caught mid-climb. Mostly, it isn't. The middle of the ladder stays stubbornly bare while both ends crowd with objects. It's the kind of pattern you'd expect if many of the giants never climbed the ladder at all, but started near the top. Then, in the last few years, the problem got deliciously worse because the James Webb Space Telescope started looking even deeper into the past, and instead of finding calm, it found more monsters. Webb has now identified quasars and active black holes within the first billion years of the universe. some within the first 500 million, already weighing millions to billions of solar masses. Each one tightens the same knot: less time, more mass. There's even a candidate at around redshift 10, an object called UHZ1, whose X-ray glow suggests a black hole nearly as massive as all the stars of its own host galaxy put together, a baby galaxy that is, impossibly, almost all black hole. So the field has been forced toward a striking idea. If black holes didn't have time to grow from small seeds, maybe the seeds weren't small. The leading version is called direct collapse, and it makes a good bedtime story, because it describes a kind of birth the universe may only ever have managed in its first few 100 million years, never before, never since. Picture the early universe, vast clouds of pristine hydrogen and helium, the raw material of everything, unpolluted by the heavier elements that stars would later cook up. Ordinarily, a giant cloud like that fragments as it collapses, breaking apart into thousands of ordinary stars. That's why we have galaxies full of small suns instead of a few colossal ones. The fragmenting depends on the cloud's ability to cool, and cooling, it turns out, depends heavily on those heavier elements and on certain fragile molecules. But in just the right early universe conditions, a pristine cloud bathed in ultraviolet light from a violent neighbor that destroys the molecules it needs to cool and fragment. The cloud can't break apart. It has no choice but to collapse whole. Hundreds of thousands of solar masses of gas folding inward as a single object. Briefly, perhaps, a supermassive star, swollen and unstable, living fast and dying almost immediately, and leaving behind not a 20 solar mass black hole, but a seed of 10,000, even 100,000 suns. Start the race from 100,000 instead of 20, and the arithmetic breathes. The number of doublings drops, the timeline relaxes. The monsters of the early universe stop being impossible and become merely extreme. That's why evidence for heavy seeds, objects like UHZ1, has been greeted with such quiet excitement. It suggests the universe's biggest black holes were never grown from stellar dust at all. They were born already enormous through a door that closed 13 billion years ago. There are wilder ideas too, at the speculative edge. Black holes formed in the first second of the Big Bang itself, before there were stars to die. Episodes of Super Eddington feeding, where gas smothers the light's resistance faster than radiation can fight back, and the speed limit bends. Webb has already caught at least one small early black hole, apparently feeding at 40 times the Eddington rate, briefly, unsustainably, but genuinely. Each of these ideas might hold a piece of the answer. Nobody yet knows the mix. And there is one more layer to the mystery of TON 618's size, one that has nothing to do with time and everything to do with a ceiling. It turns out black holes and their galaxies grow up together. Across every galaxy, astronomers have weighed carefully the central black hole's mass, tracks the mass of the galaxy's central bulge of stars with eerie consistency. The black hole comes out at roughly 0.1% to 0.5% of the bulge, again and again, in galaxy after galaxy. It's called the M-sigma relation, and it's one of the deepest patterns in extragalactic astronomy, because on the face of it, it shouldn't exist. A black hole, remember, doesn't reach out. Its gravity dominates only the innermost specks of its galaxy. The stars in the bulge, thousands of light years away, have never felt it. How do the two ends of the system know about each other? The suspected answer is the quasar itself. When the black hole feeds, its blaze and its winds don't stay home. They pour out through the whole galaxy, heating gas, driving it outward, and eventually shutting down the very star formation and the very feeding that made them. The black hole regulates its galaxy, and in doing so, regulates itself. The monster and its home negotiate each other's growth over billions of years, and the M-sigma relation is the signed agreement. Now, apply that agreement to TON 618. A black hole of 66 billion suns at 0.5% of a bulge implies a host galaxy of staggering scale, a system of trillions of stars, among the greatest galaxies that could exist. And the light around the quasar hints that the host is indeed vast. The glare sits inside an enormous glowing envelope of hydrogen, a nebula reported to span hundreds of thousands of light years, larger than the entire Milky Way, shining because the quasar's radiation has set its whole galactic neighborhood alight. Whatever TON 618 lives in, it is not an ordinary galaxy. It may be one of the largest single structures of its era. And here is the ceiling. In 2016, the astrophysicist Andrew King published a calculation with one of the best titles in the scientific literature. How big can a black hole grow? The answer wasn't forever. A luminously feeding black hole needs its accretion disk, and the disk itself has a breaking point. Make the black hole massive enough, and the disk becomes so large and so cold at its outer edges that it can no longer hold together as a smooth flow of gas. It fragments under its own gravity and condenses into stars instead. The pantry doesn't just run low, it turns into things that no longer fall in. King's arithmetic put the ceiling at around 50 billion solar masses for a typical black hole, stretching toward 270 billion only in the most extreme, fastest spinning cases. Look at where TON 618 sits. 50 billion is the standard ceiling, and TON 618's measurements straddle it. The revised estimate of 40 billion presses up beneath the limit. The classic 66 billion figure pokes through it, explicable only if the black hole spins fast. Either way, the conclusion is the same, and it reframes everything we've said tonight. TON 618 is plausibly close to the biggest black hole the universe's own physics permits to shine. We happen to find the thing that sits at the limit. Somewhere near that mass, the engine of growth dismantles itself, the fire eats its own fuel line, and the age of the great quasars ends by law, not by accident. We didn't just find a monster, We may have found the wall. What we know is this. Ton 618 sits at the summit of the problem, the heaviest measured member of a family of objects that all seem to have arrived too early, too large, to a universe too young to have raised them the ordinary way. It is a 66 billion sun answer to a question we haven't finished asking, and the whole time we've been puzzling over its weight, it has been doing the one thing it does better than anything else in the universe: shining. Let's return to that number from earlier, because we rushed past it. 140 trillion suns. That is the estimated luminosity of Ton 618, the total light pouring out of the quasar moment after moment for at least as long as we've been able to look. It's the kind of number that needs translating, so let's translate. Our sun is an ordinary star, but it is not a small thing. Every second, it converts around 4 million tons of matter into pure energy. The light from that one star at a distance of 150 million kilometers is strong enough to burn your skin in an afternoon, drive every storm on Earth, and grow every leaf that has ever grown. One star. The Milky Way holds a few 100 billion stars. Add up all of their light, every sun in every constellation, the whole glowing wheel of our galaxy, and Ton 618 by itself outshines it several hundred times over. One object, brighter than hundreds of galaxies, and the engine producing all of it is the darkest thing that can exist. We touched on how the trick works. The accretion disk, friction heating the spiraling gas until it glows. But the scale of the machinery around Ton 618 deserves a moment of its own. The disk feeding a black hole this size is not a whirlpool the size of a solar system, like the modest disks around ordinary black holes. Estimates for quasars in this class describe disks that could swallow whole planetary systems in their thickness alone, spinning storms of gas wider than the distance between stars, with inner edges moving at meaningful fractions of the speed of light. Temperatures in the inner disk run to hundreds of thousands of degrees, hot enough that most of the blaze comes off not as visible light but as hard ultraviolet, the kind of light that would strip the atmosphere off a world. That ultraviolet, in fact, is why anyone in Puebla in 1957 noticed anything at all. Here's the lovely closed loop of it. Light left the disk of Ton 618 as fierce ultraviolet. 10.8 billion years of cosmic expansion stretched it, reddened it, down through the spectrum. And by the time it fell on that glass plate at Tonantzintla, it had been stretched to precisely the blue-violet that made Iriarte and Shavira pause over one dot among thousands and write decidedly violet in the margin of their survey. The color that got it noticed was a fossil of the violence that made it. The wound was the signature. There's something else hiding in the brightness, a fact I find genuinely difficult to hold, and I want to hand it to you carefully. To shine at 140 trillion suns, an accretion disk has to be fed. The arithmetic of that feeding is straightforward, and it is monstrous. A luminosity like that implies Ton 618 swallowing on the order of several tens of solar masses of matter per year. Call it one sun's worth of matter every week or two. Every week or two, at the moment whose light we are seeing, Ton 618 consumed the equivalent of our entire sun, all of it. The mass of a star that could hold 1,300,000 Earths, spiraling through the blazing disk, flaring one last time and crossing the horizon into silence. Then, a week or two later, another and another. It had, by the time of the light we see, apparently been doing this, with pauses and stutters, but relentlessly, for billions of years. The brightest thing we have ever catalogued is the sound, translated into light, of the universe being permanently subtracted. The disk isn't even the whole of the violence. Remember how Ton 618 was unmasked, not by its light, but by its radio noise, picked up at Bologna in 1970. That radio emission is the signature of jets, twin beams of matter flung outward from the black hole's poles, launched by the twisting magnetic fields of the inner disk, moving at very nearly the speed of light. Quasar jets are among the largest coherent structures anything can build, beams that stay focused not for light years, but for hundreds of thousands of light years, drilling out of their host galaxy entirely and inflating vast, glowing lobes in intergalactic space. A black hole the size of a solar system, aiming a structure larger than its whole galaxy. When we say the monster is loud, this is what loud means. It was audible in radio light across 10.8 billion light years to a species that had only just built its first radio telescopes. Ask, just for a moment, what all this would mean up close. And this is speculation, the honest kind, but the numbers underneath it are real. A planet orbiting a star in the quasar's host galaxy, even thousands of light years from the center, would have had Ton 618 in its sky, not as a point of light, but as a presence. A beacon outshining the planet's own sun in raw output by orders of magnitude, compressed into a single, searing, star-like point. Close enough in, the ultraviolet blaze would sterilize surfaces and strip atmospheres. Astronomers genuinely debate how large a dead zone a bright quasar carves in its host galaxy. Life, if it ever arose in that galaxy, likely had to wait, as perhaps life everywhere had to wait, for the fires of cosmic noon to burn down. It's possible to read the quiet of today's universe, the very quiet that lets you sleep under a dark sky, as a late chapter that follows the storms. We live in the calm the monsters left behind. And here is where tonight gets personal, in the one way a 10 billion light-year object can. You can see it, not in a photograph, not in an artist's rendering. The actual light, the real photons that left that disk 10.8 billion years ago. Ton 618, despite its distance, shines at around apparent magnitude 16 in our sky. That's far too faint for your eye and beyond small telescopes. But a serious amateur instrument, the kind of large reflector that a dedicated backyard astronomer saves up for 16 or 20 inches of mirror under a properly dark rural sky, can genuinely reach it. Think about what that means. Somewhere, In Canes Venatici, on a moonless spring night, a person with patience and a star chart can put their eye to an eyepiece and gather onto their own retina light that is more than twice as old as the Earth. Photons that were emitted before our sun existed, that crossed the universe while our galaxy was assembling, that outlived their own source's era entirely, ending their journey not on a glass plate in Puebla, but on the living cells of a human eye, in a field, at night, next to a thermos of coffee, the faintest smudge visible, the heaviest thing ever weighed. The universe does not owe us moments like that. It offers them anyway. One last translation before we leave the brightness behind, because there's a simple way to feel what 140 trillion suns means, and it involves bringing the monster home. Suppose Ton 618, quasar and all, sat where Sagittarius A star sits, at the center of our own galaxy, 26,000 light-years from your bedroom window. Ignore, for the sake of the picture, the banks of dust that hide our galactic center. What would we see? Not a glow, not a smudge, a point. The disk would still be far too small to resolve with the naked eye, but a point of light roughly 25 times brighter than the full moon. A pinprick in the constellation Sagittarius, intense enough to read by, sharp enough to cast crisp shadows at midnight, bright enough to remain plainly visible in the blue sky of noon. Every night of your life it would hang there, never twinkling, never moving. The single overwhelming fact of the sky, one dazzling dot carrying more light than every other star visible from Earth combined, thousands of times over. There would be no such thing as a dark night anywhere on Earth, ever. Whole religions would be different. Astronomy would have started centuries earlier. Nobody on this planet would ever have needed to be told that something vast lives at the center of the galaxy. It would be the first thing every child noticed, and the last light every person saw before closing their curtains. That is the object we're discussing. The distance of 10.8 billion light-years is the only reason it's a curiosity in a catalogue instead of the master of our sky. But every one of those photons is old. That's the catch in all of this, the quiet, patient catch that we've been stepping around all night. Everything we know about Ton 618, everything I've told you, the mass, the blaze, the feeding, all of it is news from 10.8 billion years ago, which raises the last question of the night, and the strangest one. What is Ton 618 now? Here is the truth underneath all astronomy, the one that tonight's object pushes further than almost any other. We do not see the universe as it is. We see it as it was. Light is fast, but the universe is wide, and every glance upward is a glance backward. You've never seen the moon as it is, only as it was a little over a second ago. The sun, 8 minutes ago. The nearest stars, years ago. Ton 618, 10.8 billion years ago. That's not a delay, that's a different universe. The light we receive from it left when the cosmos was around 3 billion years old, a fifth of its current age. Since that light departed, the universe has more than tripled its age. Whole generations of stars have been born, burned, and died. Our sun and every planet around it formed in their entirety while that light was in transit. Life on Earth began. Oceans rose and vanished. Continents drifted apart and collided, and everything you have ever cared about happened, all of it, while those photons were crossing the gap. So when we ask, what is TON 618 now? We're asking a question the universe has not yet allowed us to answer, and won't for another 10 billion years. But physics lets us make a confident guess. And the guess is beautiful, in a melancholy sort of way. The quasar is almost certainly dead. Quasars are not permanent. They are a phase, the loud adolescence of a galaxy, lasting tens of millions of years at a stretch, perhaps totaling a few 100 million years across a galaxy's whole life. A quasar shines only while the black hole feeds, and feeding at that scale eventually exhausts the pantry. The gas runs out, swallowed or blasted away by the very light of its own consumption. The disk thins, dims, and gutters out. The most luminous thing in the catalogued universe simply stops. The galaxies around us show us the aftermath everywhere we look. Nearly every large galaxy in today's universe carries a giant black hole at its center, sitting quietly, a retired quasar. That soft orange ring in the Event Horizon Telescope image, the 6.5 billion sun black hole of M87, almost certainly a former quasar now barely snacking, and our own Sagittarius A star, so dim and calm that we struggled for decades to confirm it existed at all, may once have blazed in somebody's sky. So the picture of TON 618 today, the real today, the one whose light hasn't reached us, is probably this: a vast, aging elliptical galaxy of old amber-colored stars. At its heart, a black hole even heavier than the one we've been describing all night. It has, after all, had 10 billion more years to gather whatever came near. And around it, quiet, no blaze, no 140 trillion sun beacon. The storm we see through our telescopes burned out billions of years before the first fish moved in Earth's oceans. We are staring, transfixed, at the ghost of a fire, and the hearth went cold before our world was born. And now for the fact I've been saving, the one that for me is the strangest in tonight's whole story. I said earlier that we won't see TON 618's present for another 10 billion years. That was generous. The truth, according to standard cosmology, is harder and stranger. We will never see it. Not in 10 billion years, not ever. Here's why. The universe's expansion is accelerating. That's the discovery, made by two teams tracking distant supernovae in the late 1990s that earned the 2011 Nobel Prize and gave us the term dark energy. In an accelerating universe, distant regions are carried away from us faster and faster, And there is a boundary, a cosmological event horizon, beyond which events happening now can never send us their light. Not because the light is slow, but because the space between us stretches faster than the light can close the gap. The photon flies toward us forever, like a runner on a treadmill whose belt keeps speeding up and forever loses ground. TON 618 today sits at a present-day distance of around 18 billion light-years, comfortably beyond that horizon. Whatever it is doing right now, this instant, as you lie there, is happening in a region of the universe that has already permanently finished being able to reach us. The light we receive is old light, sent long ago from when the gap was still closable. The supply of it is finite. Over the coming eons, telescopes will watch TON 618 story play forward through a few billion more years of its history, the light already in transit, already committed, and then the story will slow and redden and fade, the final frames stretching toward infinity, like the image of something falling into a black hole. The resemblance is not a coincidence. It is the same physics. The expanding universe is doing to TON 618's galaxy, on the grandest possible scale, exactly what TON 618 does to everything that crosses its horizon. We are looking at a ghost through a door that has already closed. If you want to feel the strangeness fully, turn it around. Imagine, and this is speculation now, the gentle kind, but grounded in real numbers, a world orbiting some old star in that galaxy today. If there are astronomers there, they know nothing of the monster's glory days. To them, the black hole at their galaxy's center is a quiet, dark, mathematical fact, the way Sagittarius A star is to us. Perhaps they've traced their star's orbits and been astonished by the mass at the middle. Perhaps they wonder, as we do about ours, whether it ever raged. And if they point their telescopes toward a small, unremarkable spiral galaxy 10.8 billion light-years away toward us, they see the Milky Way as it was 3 billion years after the Big Bang, before the Sun, before the Earth, before any of this. Two galaxies looking at each other's baby pictures, each unable to ever see the other grown. There's one more chapter in TON 618's story, and it hasn't happened yet. It's the longest chapter of all, and it belongs to the deep future. Because black holes have one more way to grow long after the gas runs out, and it's the way that never stops working. They merge. When galaxies collide, and galaxies never stop colliding, even in the emptying universe, our own Milky Way and Andromeda are due to meet in around 4.5 billion years. Their central black holes eventually find each other. They spiral together over eons, whipping around one another faster and faster, radiating away their orbital energy as gravitational waves ripples in space-time itself. The same ripples our detectors have been catching from smaller mergers since 2015. And at the end, in a final fraction of a second, the two horizons touch and become one. Two giants make a greater giant, with no Eddington limit, no fragmenting disk, no ceiling. Merger growth answers to none of the rules that stop feeding. In the deep future, whatever Ton 618 has become will keep gathering its neighborhood this way. Its host galaxy swallowing lesser galaxies, its black hole absorbing their black holes, growing by collision in the dark, silently forever. The universe's era of stars, the age we live in, bright with fusion, is temporary. Star formation is already winding down, galaxy by galaxy. The cosmos makes fewer new suns each eon than the eon before. Trillions of years from now, the last small red stars will exhaust themselves and the age of starlight will end. What persists after that, outlasting everything else, are the black holes. The ultra-massive ones, the Ton 618s, will be the final great structures of the universe, dark anchors in an emptied sky, patient beyond every other patience. Even they are not forever. If our understanding of physics holds, black holes leak unimaginably slowly through the quantum process Stephen Hawking described, giving their mass back to the void, one whisper of radiation at a time. For a black hole the size of Ton 618, the timescale for that evaporation is a number so large it's almost a joke to write down, on the order of 10 to the 100th power years, a 1 followed by 100 zeros. If every year of that span were compressed into a single second, the compressed version would still be unimaginably longer than the current age of the universe. Ton 618 will be among the last things. When it finally fades, somewhere in that inconceivable distance of time, it may be one of the final events that ever happens. The heaviest object we've ever weighed is also, in the deepest sense, the most enduring thing we have ever laid eyes on. Long after every star we can see tonight has gone dark, it will still be there, silent, invisible, and vast, carrying inside it, in whatever way a black hole carries anything, one sun's worth of matter for every week or two of a feast that ended before our world began. Now, as we finally come to the end of tonight's journey, let's drift back the way we came, back across 10.8 billion light years, back to a small blue planet, back to a dark hillside in Puebla in 1957, where all of this started with 2 astronomers and a speck of silver on glass. Because that, in the end, is the part of this story that belongs to us. We are a species that has existed for the blink of a cosmic eye, on a world that formed while Ton 618's light was already more than halfway here. We have never left our own neighborhood. Our fastest machine, flying for 50 years, has traveled less than 1 light day. By every physical measure, we are small in a way that numbers can describe, but minds cannot hold. And yet, from this one small world, we noticed a violet dot among 10,000 others, and we wondered about it. We weighed an object we will never visit, using nothing but the stretched fingerprint of hydrogen. We caught the universe's heaviest black hole in the act of being impossible, And instead of looking away, we started rebuilding our theories to make room for it. We photographed a horizon 55 million light-years away. We are, right now, pointing a mirror at the first few 100 million years of time itself and finding monsters and delighting in them. TON 618 doesn't know any of this. Nothing we do will ever matter to it. It has swallowed suns beyond counting, and it will outlast the age of stars. And it has never, in any sense, noticed anything at all. But we noticed it. That's what we are as far as anyone can tell, the noticing part of the universe, the part that looks at a hole in the sky 40 Neptune orbits wide and feels something. The part that turns violence into knowledge, and knowledge into wonder, and wonder into a quiet voice in the dark, telling the story to someone who's almost asleep. They found it on a photographic plate and thought it was a star. They found it again in a radio survey and realized it was a fire. They read its spectrum and discovered it was the heaviest thing ever weighed. And they ran the numbers and understood that it shouldn't exist at all, and that somewhere in that impossibility, the universe was telling us how the first great things were born. Every question it answered opened a deeper question. Every measurement made it stranger. That's not a failure of science, that's the whole point of it. The universe is not a puzzle that shrinks as you solve it. It grows. Thank you for spending tonight here, drifting alongside TON 618, from a grape-sized Earth to a horizon 2 weeks wide at the speed of light, from a Mexican hillside to the end of the age of stars. If this journey moved you, or made the universe feel a little larger and your own troubles a little smaller, take a moment whenever you surface to like the video and subscribe. It genuinely helps this quiet corner of space keep going. And now, wherever you are, let the numbers go. You don't need to hold them anymore. Somewhere overhead, in the constellation of the hunting dogs, just off the handle of the Big Dipper, there is a point in the sky where 10.8 billion-year-old light is arriving right now, landing softly, unnoticed, on rooftops and oceans and the closed curtains of rooms like yours. Light from a fire that went out before the Earth was born, still faithfully delivering its message that the universe is older, stranger, and more patient than anything it has ever contained. It will still be arriving tomorrow night and the night after. It can wait. Sleep well.